My name is Ralf, and I'm happy to present our work, Failure Prediction at Runtime for Generative Robot Policies, accepted to NeurIPS 2025. Humans need to continuously learn about the world, especially as children. In a similar way, generative robot policies, including large-scale vision language action models, cannot handle every environment or task zero-shot. When faced with novel or ambiguous situations, these models may behave unpredictably or even unsafely. To prevent this, robots should be able to recognize when they don't know and proactively ask for help. So, our key objective is to detect situations where a generative policy exhibits high uncertainty and is likely to fail at its task. We propose Fiper, a general framework for failure prediction at runtime designed to work with any generative imitation learning policy. Fiper computes two complementary scores. The first detects out-of-distribution observations, capturing when the robot encounters something unfamiliar. The second measures uncertainty in the generated action chunks, signaling when the policy is unsure about what to do next. The observation-based score is learned offline, and we calibrate both scores using only a small number of successful in-distribution rollouts. During deployment, Fiper aggregates these scores over sliding windows to enhance robustness. A failure is predicted only when both modules raise a warning, reducing false alarms. Importantly, Fiper is task agnostic and does not require access to the policy's training data, making it ideal for policies pre-trained on large-scale datasets. And crucially, Fiper needs no examples of failures, which are often unsafe or expensive to collect. Next, we'll take a closer look at how each of the two scores is computed. Our observation-based score detects out-of-distribution inputs through random network distillation, applied directly in the policy's observation embedding space. We train a predictor network to match the outputs of a randomly initialized target network on in-distribution data. At runtime, if the difference between their outputs is high for a new observation, this suggests the input is out of distribution relative to what the policy has seen before. We then aggregate the scalar score over a sliding window to smooth out noise. If the aggregated score exceeds a threshold, the observation-based module raises a failure warning. Since imitation learning policies may generalize to a certain extent, out-of-distribution detection alone is not robust enough and can result in many false alarms. Therefore, we also measure uncertainty in the policy's conditional action distribution. In human demonstrations for imitation learning, multimodal action distributions are common. Since action multimodality usually has a discrete nature and is observation-dependent, variance is not a good measure of uncertainty. Instead, we assess mode sharpness through entropy, which better captures uncertainty about the correct actions to take. Since computing true entropy is intractable, we introduce an action chunk entropy score, which can be computed efficiently from a batch of generated action chunks. We aggregate and calibrate this score in the same way as our observation-based score. We use conformal prediction to calibrate both thresholds based on only a few successful in-distribution rollouts. Fiper predicts a failure only when both scores exceed their thresholds, ensuring robustness against temporary high uncertainty in the input or output. We show that our calibration method provides an upper bound on the false alarm rate in in-distribution settings, which is an important property when failure warnings are costly. We conduct experiments across different environments. Standard metrics like accuracy or detection time alone are insufficient to fully capture a failure predictor's performance. Thus, we introduce time-step-wise accuracy, a new metric that combines accuracy and detection speed into a single value. We show that our scores spike specifically in case of task failure, rather than out-of-distribution situations, which is critical for robust failure prediction. Compared to baselines, Fiper achieves the highest time-step-wise accuracy and is both more accurate and faster at predicting failures. Here we show example rollouts, illustrating how Fiper can predict different kinds of task failures across diverse environments. In summary, Fiper is a general framework for fast and robust uncertainty-aware failure prediction for diffusion policies and VLAs.